this course on accelerator physics. So this is module 2 of the course on accelerator physics, in which I will be covering about linear accelerators. So you've already studied about DC accelerators, where acceleration is done using DC fields. Now we'll study about RF accelerators, where acceleration is done using time varying or RF fields. So this module consists of 13 lectures, and let's get started with the first lecture, which is basically introduction and some basic concepts that you will be requiring during this course. Listed here is the references that I will be using. So the first book, RF Linear Accelerators, I will be using this book widely. This is by Thomas Wangler. The other books that I will be using are Accelerator Physics by S.Y. Lee, Particle Accelerator Physics by Helmut Weidmann, then Introduction to Accelerator Physics by Arvind Jain, and for the superconducting accelerators portion, I'll be referring to these two books, RF Superconductivity for Accelerators and RF Superconductivity by Hassan Batansi. In addition to these, you can also refer to the proceedings of the CERN Accelerator School and the US Particle Accelerator School, which is available by online. So these, I've already given here the websites where you can refer to. These schools have been running for various years, and they have a lot of good information on accelerator physics. So you can use this also. So here's the basic outline of the course on linear accelerators. So first I will be giving you an introduction and basic concepts. Then we'll learn about RF acceleration, that is how acceleration is done using RF fields. Then how these RF fields are generated in Linac cavities. So basically we use the electric fields associated with the electromagnetic waves in the cavity. So for that we learn about electromagnetic waves, their propagation in free space between two parallel conducting planes, waveguides and cavities. We learn about different accelerating structures, from the simple pillbox cavity to the drift tube Linac and the complex radio frequency quadrupole accelerator. We'll also learn how acceleration can be done using traveling waves as well as standing waves. Having learned all the accelerating structures, we'll learn about the dynamics of the beams in the transverse direction, that is transverse in the direction of propagation of the beam, and then their dynamics in the longitudinal direction. And then finally about superconductivity in Linacs. So let's start with some basic definitions. The charge particle acceleration basically means to increase the kinetic energy of the charge particles by the application of an electric field. Why only electric field? That we'll understand in a moment. So we accelerate charge particle beams in the accelerator. What is a charge particle beam? So basically it is an ensemble of charge particles that satisfies the following conditions. Not all collection of charge particles can be called a beam. Only those collection of charge particles that satisfies the following conditions can be is known as a beam. So the particles in the beams, they should have high kinetic energies as compared to the thermal energies. Small particles have some thermal energies. So to qualify as a beam, the kinetic energy of the beam should be quite high as compared to the thermal energy. The spread in kinetic energy of the charged particles is small. So basically, let's say if you have a collection of charged particles and one particle is at 10 MeV, another at 5 MeV, and another at 10 MeV. This again does not qualify as a beam because there is a huge spread in the kinetic energy of the charged particles. To qualify as a beam, the spread in the kinetic energies should be very small. Finally, the beam particles, they move in one direction with limited extent in the transverse direction. So let's say this is a beam and it is propagating in the Z direction, which is a direction coming out of your screen. So the X direction and in the Y direction, the velocities of the particles, so Vx and Vy, okay, so these should be very, very small as compared to the velocity in the Z direction. So they should have limited extent in the transverse direction to the direction of propagation of the beam. Then it qualifies as a beam. So you must have already studied about classification of accelerators. Let me just list it down here again for completeness. So basically accelerators are classified based on the way the charge particles are accelerated. So DC accelerators use DC fields for acceleration. RF accelerators use RF fields for acceleration, or time varying fields for acceleration. Okay, so DC accelerators, basically you generate high voltage. So some methods of generating high voltage are Cockcroft-Walton, Van de Graaff, Pelletron, etc., which you must have already studied in module 1. RF accelerators are further classified into circular accelerators and linear accelerators, depending upon the path taken by the charged particles during acceleration. So when charged particles move in circular paths, they are circular or spiral paths, they are known as circular accelerators, and when they move in a straight line, they are known as linear accelerators. Module 3 will cover the circular accelerators. Some examples of circular accelerators are microtron, betatron, cyclotron, synchrotron, etc. And some examples of linear accelerators which you will study during this course are the drift tube LINAC, the coupled cavity drift tube LINAC, the RFQ, etc. So, as I said, linear accelerators or LINACs, they are devices that accelerate charged particles in a single line. Energy gain in a DC field. So the simplest way to accelerate a charged particle is acceleration in a DC field. So you simply generate a DC field, apply it between two plates, okay, and then you have a charged particle. It sees this potential difference, it sees this electric field. The force acting on the charged particle is simply force is equal to Q into the electric field. Here Q denotes N into E. So N is the total charge state. So let's say, for example, you have copper 2 positive. So here N is equal to 2. Okay, because your force acting as well as the energy gain will also depend upon what is the charge state. And E is simply the electronic charge, which is 1.6 into 10 to the power of minus 19 coulombs. So energy gain of a charged particle in the electric field generated by potential V is simply delta W is equal to Q into V. V is the potential difference. Typically, the unit used here is electron volts, and the relation between electron volts and joule is 1 electron volt is 1.6 into 10 to the power of minus 19 joule. If you want to talk in terms of higher energies, use so 1000 electron volt is kilo electron volt, and then you have million electron volt, giga electron volt, and tera electron volt. So the highest energy to which particles have been accelerated so far is 7 TeV. The Large Hadron Collider at CERN accelerates charged particles to 7 TeV. So that's the maximum energy to which the charged particles have been accelerated. Okay, so why do we talk in terms of electron volt? Why not joule? Because in our daily life we use joule. So just to give you an idea about the numbers, let's see here the energy to raise a 100-gram object by 1 meter. Okay, if you can calculate this will come out to be 0.1 kilogram into the acceleration due to gravity. Let me take it as 10 meters per second square multiplied by the distance 1 meter. So this comes out to be 1 joule. Okay, and this number, if I convert it into TeV, it's a huge number. Okay, remember the maximum energy to which charged particle has been accelerated is 7 TeV. So this is much greater than that. Okay. Okay, again now let's see the energy to power a 100-watt bulb for just 1.6 nanoseconds. That is 1 TeV. Okay, so these numbers which in our daily life we use, so compared to that, if you see the energies of the charged particle, so they are huge. So you can calculate the energy of the proton traveling with a velocity almost close to the velocity of light. Okay, so that is 5.7 GeV, which is only 9.1 into 10 to the power of minus 12 joules. Okay, so it's quite a small number. Okay, however, when we are talking of a beam, the bunch of a beam in an accelerator has large number of particles. Okay, of the order of 10 to the power of 10 to 10 to the power of 12. So total beam power is very high. Okay, so here the velocities to which we are accelerating is very high. Okay. However, the mass of the charged particles is quite low as compared to objects in our daily life. So that is why their energies may appear to be smaller than that compared to what we use in our daily life. So joule is too big a number to denote the energies of these particles. Hence, we use electron volt here. Okay, so why do we need to go to RF accelerators? Because DC accelerators have certain disadvantages. The maximum energy in the DC accelerator is limited by the maximum voltage that can be generated. Okay, so the energy gain depends upon how high a voltage you can produce and sustain. So this is limited. Maximum you can go to maybe just about 20 to 30 million volts in a DC accelerator. Also, this high voltage generated, you cannot use it more than once or twice, as in the case of tandem accelerator. Okay, so you cannot use this voltage generated again and again. So it's not possible to have a circular DC accelerator. Okay, let's say you've generated a DC voltage. Okay, so you've applied some potential difference, okay, of V, and you've generated a electric field. The charged particle sees this field and this is the energy gain. Okay, and now if you would say that let me bend this and bring it back again and accelerate it again, it's not possible, because you see that the DC accelerators, they use electrostatic fields for acceleration, and electrostatic field is a conservative field. So if you see from Maxwell's equation, curl of E is 0 or integral of E dot dl is 0. That means it is this is independent of the path taken. It depends only on the initial and final coordinates. Okay, so if I gain some energy delta W here, in going back here I will again lose that energy. So there will be no net energy gain, and it does not matter if I go back to this point in this manner or in this manner. Okay, so the field generated by a DC voltage cannot be used more than once for acceleration or twice in the case of tandem accelerator. Okay, so it's not possible to accelerate charged particles to very high energies using DC accelerators. So what is the solution? The solution is to use an RF accelerator. The RF accelerator uses time varying electric fields for acceleration of charged particles. So if you see the electromagnetic spectrum, okay, so this is the frequency, okay, and the frequencies used for acceleration, they lie in this range, typically from few megahertz to tens of gigahertz, and this lies in the radio frequency region. Okay, so that is why this is known as a RF accelerator. So it's using time varying electric fields for acceleration, and since the frequency lies in the radio frequency region, it is known as RF accelerators. And as you've already seen, there are two types of accelerators, RF accelerators. One is the circular accelerator, the other is the linear accelerator. So the circular accelerators, the charged particles move in a circular or spiral path, whereas in a linear accelerator, they move in a linear path. In the circular accelerator, the same voltage can be used multiple times for acceleration. Okay, so you can have a circular accelerator and you can have a accelerating cavity here. You can keep bending the particles and bringing it back here again and again. So the same voltage generated can be used again and again. The fields are time varying, so the field is no longer conservative. Okay, so unlike the DC accelerator, you can use this voltage again and again for acceleration. The linear accelerator, on the other hand, it's a single pass machine. The charged particles will pass through it for a single time. Okay, the voltage generated here is used only once for acceleration. Okay. The circular accelerators cannot handle very high beam currents, whereas the linear accelerators, they can handle very high beam currents as well as they can run in high duty cycle. So we'll learn about the duty cycle in this course. The circular accelerators, they exhibit synchron radiation losses. So when charged particles they bend, they emit a radiation known as synchrotron radiation. So these synchrotron radiation cause loss in energy, which has to be compensated in the accelerator. Since there is no bending involved in the linear accelerator, so there is no losses due to synchrotron radiation. In the circular accelerators, since charge particles are moving in a circular path, so the extraction becomes difficult, whereas extraction is simpler in a linear accelerator. So circular accelerators, they require lesser cavities because you can use the same cavity again and again, whereas the linear accelerators require large number of cavities. So this makes linear accelerators expensive and they need more space, whereas circular accelerators are less expensive and need less space. So the Large Hadron Collider at CERN that I was talking about, which accelerates charged particle to 7 TeV, so it has a circumference of 27 kilometers. Okay, so you can imagine that if it was a linear accelerator, how long it would have been. So when you're building very large energy accelerators, it is better to go for circular accelerators. So some examples of circular accelerators are cyclotron, synchrotron, and some examples of linear accelerators are DTL, RFQ, etc. Linear accelerators have various applications. Okay, so they range from small accelerators to huge accelerators. So, and they are widely used for a variety of applications. Okay, the main applications are medical applications. So yeah, here they are used both for therapy. So that means treatment of cancer using X-ray radiography and proton or ion radiography, and for diagnostics. So there are certain, they are used to produce certain isotopes which can be used for the diagnosis of diseases, mainly cancer. They have various industrial applications. Okay, so irradiation of food to improve the shelf life, then sterilization. Then they are also injectors to large synchrotron accelerators and spallation neutron sources. So the Large Hadron Collider, so it's a synchrotron, it's a circular accelerator, but the injector to the synchrotron is actually a linear accelerator. So you start with a linear accelerator and then inject it into a synchrotron. They are also used for accelerator driven systems, which I'll talk about in a moment. So X-ray radiography. So here is a picture of a linac. The electron linac, it hits a target, and here X-rays are produced. These X-rays are then used to irradiate the cancerous tumor in the patient's body and kill the cancerous cell. So these are used in several hospitals for treatment of cancer. So nowadays proton and ion therapy is also gaining a lot of importance for treatment. The advantage of proton therapy or ion therapy is that if you see the depth dose curve, so if you see for X-rays, you see that initially it is high and then the dose decreases as the depth increases. Okay, so this is for different energies of X-rays. Similar for electrons. So the electrons deposit all the energy at just a few centimeter depth of the tissue. However, if you see the depth dose curve for the proton beam, we see that initially the dose is very less and then it suddenly peaks and then again goes to zero. So this is an advantage where your tumor is lying deep inside the body. So let's see here, for example, there is a tumor here, and if you irradiate it by X-rays, so here the healthy tissues are also getting irradiated, and then the cancerous cells are destroyed, and then the healthy tissues here again they get irradiated. So lot of healthy tissues are irradiated, which is undesirable. Whereas if you use the proton therapy, or you can use some ion beam also here, the advantage is that it will deposit all the dose here. So, and the depth of this peak, which is known as the Bragg's peak, can be changed by changing the energy of the proton or ion beam. So you see that it is this is very advantageous, and it is now being used for treatment of cancer because of the advantages that it offers. So in India, we have one such machine at the Apollo Hospital in Chennai, and many more are coming up. Then, as I said, they are also used for diagnostics. So here they are used for the production of isotopes for positron emission tomography. So this is a diagnostic technique for finding out the location of a cancerous tumor. So we use accelerators to produce these isotopes which are listed here. Okay, so these are all positron emitters, and they have very short half-lives. So fluorine, if you see, it has 110 minutes. So what is done is that this isotope, along with the glucose in the form of FDG, is injected into the patient's body. And so this glucose has a tendency that it is tumor seeking. So it goes and sits into the tumor, and at the location of the tumor, let's say here, the fluorine 18 in the fluorine 18 here, it will emit positron, and there are a lot of free electrons around here. So this positron will immediately combine with the free electron here, and annihilation reaction will take place, emitting 2 gamma in the opposite direction. There is a series of detectors here which can simultaneously detect these gamma, and from this the exact location of this tumor can be pinpointed. So this is a very useful technique for diagnosis of tumors. So these are the isotopes that are generally used for the diagnostic. Then there are lots of industrial applications: sterilization of medical devices, food pasteurization, then cross-linking of polymers to improve their strength, environment remediation. So there is the sludge water treatment to make it germ-free and bacteria-free. Then electron beam induced crystal defect. So coloring of gemstones, you can actually change the color of the gemstones by treatment with radiation from an accelerator. Then radiation processing of foods. Okay, so it helps in sprout inhibition. So it improves the shelf life. Then hygienization, delay in ripening. Okay, so wide variety of applications are there for the accelerators. Then they are also used as cargo scanners. So these are the cargo containers which are huge in size, and if they have to be inspected manually, it would take a large amount of time. So they have to be scanned in a very short time, typically about a minute. So we have here electron accelerators, and then they hit a target and X-rays are produced, and these X-rays, they can scan through the they can very quickly scan through the cargo container and reveal its objects. So in this picture, for example, you can see that the declared object was something else here, but inside it was actually used for smuggling humans. So it's very useful way to scan these cargo containers in a very short amount of